All right, I'm going to go ahead and make a video key for Recitation for Organic Chemistry 2 for Friday, February 21st. The first one, I actually did this on last week's recitation, but in case you didn't have a chance to get to it, I just went ahead and added it in. But this one is new, so this is a new problem that you haven't had the chance to do yet. So I'll go ahead and give you the key to that. So the first step in, you know what, a thought that I just had that I think will be helpful is sometimes I think students are unsure what to do. Like, how do you know what reaction it could be? You know, it's like you see this and you see this, and we're in the chapter on Diels-alder, so it could be Diels-alder. It could be the 1214 edition, how do you know? And the thing I think about is I look at the options given to me, like I look at the reagents and try to get clues about what it could be. So if you think about all the reactions that you learned from OChem 1, you learned about acid-base reactions, and you learned about addition to alkenes, and you learned about radical reactions, and SN1, SN2, E1, E2. And then in this semester so far, we've learned additions to carbonyl carbons, and redox, which was in the same kind of vein. And then we've learned Diels-alder. And then we've learned these 1, 2, 1, 4 additions. And so if I was on a multiple choice test, for example, how do I know what to do with this question is I sort of mentally run through, like, what all could this be? And there is an acid, but there's not a clear base. So I'm not immediately thinking that this would be an obvious acid-base question. This could be addition to alkenes because we have an alkene and we have something that went out across an alkene. So I'm like, oh, this could be it. So sort of put a check mark next to that one. That's an option. It could it be a radical reaction? We don't have heat or light, so it can't be a radical initiator. So I'm sort of like crossing this off the list. It can't be this. This is a maybe. It definitely could be the alkenes. There's not a good nucleophile or good leaving group, so I don't think it's SN1, SN2, E1, or E2. Additions to carboxylic acids or redox, well, we don't have any alcohol, so that doesn't really make sense. And we don't have any oxidizing agents, so I don't think it's any of that. So it could be Diels-alder. We do have a diene, but we don't have a dienophile, which would need a double bond, so I'm eliminating that. And so it could also be 1, 2, 1, 4 addition. Well, these are two of the same types of reactions. So based on that, I'm going to say, okay, the 1, 2, 1, 4 addition is sort of like an advanced version of the just addition. It's an advanced addition reaction. So if it has the option to do that, then that's better than this. And the first step in that is an acid-base reaction, but that's not where it stops. So that's how I'm eliminating acid-base. So if you're ever not sure, okay, I have these two reagents, what am I going to do with them? That's kind of how you process through. Think about all the reactions that you've learned, and are there any clues about what this might be based on that? And so that's how I kind of decide when I come at a question of like, okay, what do I do with it? Okay, so now I'm going to erase all this and have your HCl. Oh, I already drew these. And you know what? I will color code because I think people find that helpful. So you can kind of see where the bonds go. And the first thing that happens is the hydrogen adds here with the electrons that used to make up that double bond, and then now the carbon adjacent to it, it only has one hydrogen bonded there, so the formal charge right there is positive. And now this has a resonance structure. Oh, and chlorine, let me draw in my lone pairs. Chlorine is becoming negatively charged. So these are the two positions that the chlorine could attack. So this chlorine could attack, oh, I put that in the wrong place. This chlorine could attack right here, or it could attack right here. And so the product I would get from that would be for this one. And for this one. I'm going to draw it in purple. Okay, so these look like they are, like you might initially think, okay, so we have a thermodynamic and kinetic, but if you rotate this just slightly like this, you might notice that these are the same product. So we have, or maybe instead of rotating it, a better way for you to see it is if we number it. So if I number starting at the double bond, 1, 2, 3. Oh, whoops. I accidentally erased part of this one. And then I'll start at this double bond, 1, 2, 3. For both of these, we have cyclohex 1-ene, 3-chloro. So both of these are 3-chloro cyclohex 1-ene. So these are actually the same molecule. And the reason for that is there's not a more or less substituted alkene here. It just so happened that the way that this is drawn is there's not a kinetic and a thermodynamic product. But there are still two products if you're considering stereochemistry, because this is flat. It can attack from either side of the carbocation. So technically this and this are your two products, but both of them can be achieved with the same, with either the thermodynamic or kinetic. There's not a thermodynamic or kinetic answer here. So that's the solution for that one. Okay, this one I also did on last week's recitation, so you can go back and look at that video if you want. I just posted that yesterday. And for here, which of the following reactions is capable of going through Diels-alder with ethene? So we need a diene, so 2 alternating double bonds. And they need to be an S-cis or capable of rotating into S-cis. So this one right here has alternating double bonds, and it's already in S-cis, so this one, yes. This one is locked into S-trans and can't rotate in, so this is not possible. This one, there is free rotation around that sigma bond, so you could get this structure. So this one can rotate into S-cis. So yes. This one, again, is locked in S-trans. It can't rotate, so that one wouldn't work. Okay, next question. Which of the following dienophiles would be more reactive than ethene in a Diels-alder? Consider if the groups are electron withdrawing or electron donating, and which favors a Diels-alder. So when I think of ethene, that's not very reactive. And the way, we had a slide where we talked about that this requires high heat, which isn't really favored, because then it starts to do a reverse Diels-alder. So this isn't a great dienophile. So we talked about adding electron withdrawing groups to make this more electrophilic to improve it. So I'm looking for something to be more reactive than this is to add electron withdrawing groups. And electron withdrawing groups are going to be things that take electrons away. Now, I look at this first one, and immediately we have a CH3 group, which donates electrons, and it does that through induction. It's the same thing as why a methyl group makes a positive charge more stable, like a carbocation is more stable on a tertiary than a primary, is because it's donating electron density through induction. So through induction, this is an electron donating group, so that is less reactive than just a plain ethene. Same thing here, these would donate electron density, so I would also say this is less reactive than ethene. Now this has an oxygen, which is electronegative and can pull away, and there is a resonance structure where this is a full positive. So because of that, I would say this is an electron withdrawing group, and so this is a good option that's more reactive in a Diels-alder than ethene. This one's kind of tricky. This CH3 donates through electron density, or through donates electron density through the inductive effect, but this oxygen is going to be electronegative, except it does have a resonance structure where it donates electron density. So because of that resonance structure, this is actually overall an electron donating group, and it is less reactive. And then this last one's also less reactive because it just has CH3 groups. So the only one that's more reactive, I would say, is answer choice 3, or is the third one. Okay, for each of these, draw the proper curved arrows and then predict the product of the following reaction. Okay, there's a few different ways you can draw the curved arrows for Diels-alder, so just remember that you can do it one of several different ways. You can draw the curved arrows to point where it's going to react, which that works well if you don't have the diene already on a ring. So like in this example, 1, 2, 3, 4, 5, 6, our double bond ends up right there between 2 and 3. The new bond formed between 4 and 5, and 6 and 1. And then we have our substituent on carbon 6. So I usually just isolate the ring first and then add the substituents later. On this one, again, I'm going to rotate and look like this. And these are electron withdrawing, so that's going to make this more likely to react. And I'll go ahead and draw in my curved arrows. Oh, another way you could draw your curved arrows, I'll do it this way, is by drawing this pointed here. That's another proper way. For me, that's a little bit harder to visualize, but it is useful if, like, in the next example, when the diene's already in a double bond, or in a ring, that I think this is a better way to draw your curved arrows. So I think initially it would form, see, 1, 2, 3, 4, 5, 6, this structure. And then, actually, because we have excess of this, I think it could do another Diels-alder over here. This would be sort of the initial. And then I think we would get a secondary Diels-alder where we get a reaction on this side where this acts as a dienophile again. So it would be like this and that. So I think this would be your first answer, and then this would be an additional potential just because there's excess. This one I think is harder to do. So first of all, I'm going to say I always line up my diene like this with my dienophile because I think that's easier to see. Instead of leaving it on its side, it's just like harder to visualize. And then I number 1, 2, 3, 4, 5, and 6. And this is an example where I do think it's helpful. I'm going to color code these. I think that will be a little bit easier to see. I think it's helpful to draw the arrows where it's like shows which carbon it's attacking on this, because I've seen people draw curved arrows like this and think that it reacts with itself on this type of ring. So I recommend that if there's already a ring on your diene, you draw your curved arrows like this, but technically either way is right. Okay, so that makes our basic 6-membered ring. And we got the electron right here, this one right here, and this right here. So this is 1, 2, 3, 4, 5, and 6. And now I'm going to draw the bridge between carbon 1 and 4. So that was the original ring that was already there. And then over here, between 5 and 6, we also have a 5-membered ring. So I know that's kind of difficult to see, but I think if you try drawing it out on your own and then see if you can kind of follow, like, it might help if you, like cover this up with your finger or something and see if you can see, ignoring this part for a second, see if you can see how the ring would form and then try to add it back in. Another way that it's often drawn is to make the 4-membered ring or the 6-membered ring look like this. So that's still our 1, 2, 3, 4, 5, 6. The bond between 6 and 1 came from the maroon double bond initially. The bond between 2 and 3 came from the gray bond between 1 and 2 initially. And then between 4 and 5 came from this orange bond initially. And then there was already between 1 and 4, you had this peak right here. And then you'd get the 5-membered ring formed on the outside right there. Okay, I hope that was helpful. Let me know if you have any questions. Good luck studying.